Hi guys, today what we are going to do is that we're going to see a problem on Kalman filter localization. So first, before moving on, we have to make some assumptions. So these assumptions are very essential because we make some assumptions on the model. So what is that model that we're going to create? So the very first assumption is that we're going to assume that the motion model is linear. So the motion model is linear. That is the first assumption that we make. So when we make that assumption, what happens is that your x of t, that is, we are trying to determine the location, it will be x of maybe t minus 1, yeah, and plus u of t, right? So let me put it in brackets here. So this is my x of t, and this is u of t, where x of t is my location, right? Excuse me. So x of t is location at time t, right? And then you have y of t, which would be is the input control, or let's make say it as the movement, right? As the movement that has been made by a robot. So now what we're going to do is the next assumption that you have is that the measurement noise is not Gaussian. So we're going to measure using some sensors, and we're going to say that it's going to have some noise in it, and let's say that it is normally distributed and its mean is going to be 0, and its standard deviation, or let's say the variance, right? So the variance is going to be um, 0.5 to the power of 2, which is actually 0.25. Let that be the variance. So which is the standard deviation is 0.5, and this is the now also we make an assumption that the process noise, excuse me, is Gaussian. So here we mean that the input controls that have been given mechanically, that is going to have some noise, and let's say it's a Gaussian distribution, and it's let's say its variance to be again 0.01, right? So let that be the thing. Now what we are going to do is that we want to get to know the position, right? We want to keep updating the position. Let's say the position is the one which you're trying to determine. Let's say initially you are at excuse me, at x naught. Okay, let me just make this a little bit, mm, make it center aligned. So here, let's say I want to know at time t equal to 0, that is my initial position where I'm pretty sure that its value is going to be 0. That is the thing, and the unit for x is going to be meters. So let's say uh, unit of x is meters. So we make the thing over here. And then now we have the uncertainty, right? So we are not 100% sure that it is at this particular location. So we are just going to take it as 1 meter square, right? So that is going to be my uncertainty, right? So let's put it a bit differently. Let's say this is the time, right? A time t of 0. You see the position which is in meters. Let's write it over here like this is in meters, and this is in a meter square, because you know it's like an area around that place, so it is going to be 1 over there. So now what we need to do is that we need to know at time t1. Let's take time t1. What is the thing, right? So now let the wheel encoder say that it has been moved to 1 meter. So what I need to do is that I take 0 and it has moved 1 meter, right? So I'm just going to add 1 to it. So you get the value over here. And now I'm looking at the uncertainty. The uncertainty is, it says that initially the uncertainty was 1. Now there could be the variance which I'm going to add from the noise which is coming from this. That is going to get added. And hence we have 1.01, which is the uncertainty. It has been increased a little bit. Excuse me. Now at same time t is equal to 1. So this is the reading actually coming from the wheel encoder. So it is going to tell what is it. At time t is equal to 1, we are going to get the GPS data. And the GPS data, it says that its location is 1.1. So what we need to do is that we have to find out the Kalman filter, because we're going to check how much we can rely the GPS sensor. So the wheel encoder is creating an error, GPS is creating an error, but how much can I rely GPS information compared to the one given by that? So for that, what we need to do is that we need to take the uncertainty which you have here, you're going to divide it by this uncertainty plus the variance that can be coming from the measurement numbers. And that will be the equation for Kalman filter gain. So this is my gain, or let's say it as K. K is actually standing for the gain. So now once you have this gain, the way the updated position is going to be the one which you have here, 1 plus, you're going to take this Kalman filter gain, multiply by the difference of what is told by the GPS. It says 1.1 minus the one which you have from the wheel encoder. So that will be the equation here. When I substitute that, you're going to get 1.08016. Excuse me. Now the uncertainty that you're going to have is going to get reduced. It's 1 minus the k multiplied by the position that you got there. That is 1.01. That was the earlier uncertainty. So now the uncertainty is reduced because the GPS is more reliable, and hence the information that you're going to get is much more, and hence the uncertainty is being considerably reduced here. Now again I'm going to time t is equal to 2, and I'm going to get the wheel encoder reading, and let's say that the wheel encoder says that its location is again moved by 1 meter. So in that case, what I do is that I take this value, it says it's moved by 1 meter. Now I need to find out what is the uncertainty, right? So this thing is already having a variance of 0.01. So my uncertainty would a little bit increase because of the information from the wheel encoder. Now I need to find out the K for this thing. And for the K, what we're going to do is that we're going to take the uncertainty from the okay, let me delete it here. So the uncertainty from what you have here from the wheel encoder plus this plus what you have over here, the variance, and that will be 0.4569. And now I take my calculate the one using oops, I made a mistake. Let me just delete this thing here. So first what you need to do is that first you take information from the GPS. It says around 2.3 is the information. So now I find the Kalman filter. So this is just divided by this plus this, and I get my Kalman filter gain. And now what I do is that I find out the location here. So it will be this information what you have, plus you're going to multiply it with the Kalman filter gain of the difference that you're going to have. So it says 2.3, but actually what the wheel encoder says is 2.08. So now the information is 2.18. That is the distance which you got here. And this is going to be 1 minus the Kalman filter gain multiplied by the previous uncertainty. Hence it's 0.142. So now I'm moving a little bit further to the right. So I'm looking at time t3. So I'm looking at the information from the wheel encoder. Again, let it say it is moved by 1 meter. So I'm just going to increase it by 1 meter. And now when I'm calculating the uncertainty, so the initial uncertainty is this, and it is increased by the variance that has been given by them. Now let's take the information from the GPS. Let's say the GPS says it's 3.2. So in that case, first I'll find the Kalman filter gain. So it will be the uncertainty from the wheel encoder plus the information with the variance that you have here. And this is the information that I get. Now we'll calculate the exact location. I'll use the Kalman filter gain, which is multiplied by 3.2 minus this value, and I get 3.187. Now I can calculate my uncertainty, which is 1 minus Kalman filter gain multiplied by this, and it has come. So as you see here, the uncertainty has been reduced every time when GPS is giving data, and over a period of time, it becomes much less. And this is how the Kalman filter localization works. Thank you all for watching. If you like this video, click on the like button. If you would like to watch more videos like this, you can subscribe to this channel. Feel free to give some comments. Thank you again. Bye.